Ants are fascinating insects. They communicate with each other and coordinate both their actions and movements. Each ant makes its decisions autonomously, but in doing so is subordinate to the common objective and thereby plays its part towards solving the task in hand. The delicate ants are therefore a real challenge for the Festo engineers when it comes to transferring role models from nature into the world of technology. For the first time with the BionicANTs, the behavior of ants is imitated using complex control algorithms. In this respect, it's not about a technical game for the Festo engineers, but about nothing less than the production technology of the future. In the world of Industry 4.0, machines also have to communicate with each other, make autonomous decisions and cooperate in order to be able to react flexibly to different production scenarios. The biggest challenge for the Festo engineers was to integrate all the necessary functions of an artificial ant into the smallest of spaces with as few components as possible. Our engineers overcame this challenge. Enough space was created for the rechargeable battery and room for the eyes was made in the ant's head. Such a functionally integrated design is made possible thanks to 3D printing. It would be difficult to make such an ant using conventional production engineering. 3 piezo bending transducers are used on each leg. Coated on both sides with piezo ceramics, they are able, depending on the electrical controls, to deflect by 1.5 millimeters in both directions. Clearly not enough to get an ant to walk. With the help of an elastic hinge, the Festo technicians have managed to increase the ant's step length to over 10 millimeters. The benefits of piezo elements are impressive. They work on little energy, are almost wear-resistant and can be controlled quickly. But how does a small ant robot learn to walk? The motion sequences of the ant are programmed and tested on a computer. If the ant walks smoothly on the computer, it must demonstrate during initial tests on the real model how well it can walk with its 6 legs. Taking into account that this bionic ant has only just learned to walk, it gets around really quickly. Using a 3D camera system which was developed by scientists at Delft University and adapted to the ant by Festo engineers, the ant is able to see. Combined with an optoelectrical sensor, the bionic ant manages to find its way round in the space. How does the ant determine its position when it's on the pitch? Well, for this we actually use 3 sensors. First of all, we have a mouse sensor here under its abdomen. The mouse sensor is actually the same as in a computer mouse. We can use this to track where the ant walks across the pitch. We also have a magnetometer here in its head. The compass actually shows where north is, and with this we can determine what direction the ant is headed. Here at the front we also have a camera system consisting of 2 cameras, which gives us a stereo image and means we can detect the markers on the pitch and also measure the distance to them. We can therefore position ourselves with complete accuracy on the pitch. In order to turn such demanding projects into reality, Dr. Elias Knubben surrounded himself with an international group of outstanding and above all creative engineers. Nothing goes by the book here. Every step during the development of the bionic ants represents a challenge and requires creative solutions. Even the production method for the bionic ants is unique. For the first time, components produced using 3D printing are subsequently embellished with visible conductor structures in the so-called 3D MID process. These 3D MIDs are conductive tracks printed directly onto the body, which enable us to attach all the components directly on the body, because this is naturally where there is the biggest surface and room for such things, and we therefore manage to make the ant move properly even with a low weight. The ants communicate wirelessly with each other, but what information do they have to exchange to fulfill a task they are given? The Festo team is supported by scientists from Ulm University. Professor Knut Greichen and Sebastian Henselt are specialists for measurement, control and microtechnology. Above all, the cooperative transporting of loads is a control technology challenge for the bionic ants. Which ant pushes, which one pulls? As there is no boss ant, all ants are equal here, the bionic ants have to constantly exchange information in order to move the transported goods to their destination in a cooperative manner. The assembly of the bionic ant is very simple in contrast. All the parts fit in their place as intended and can be simply screwed tight. It does get a little tricky once again when it comes to soldering the circuit board on the abdomen. This circuit board houses both the tracking system and the wireless technology for the communication between the ants. The ants are a fascinating role model from nature, where you can observe very well how it is possible to combine many individual subsystems to make a complete solution by means of collective behavior. That is precisely what we reproduced with these bionic ants. Small artificial ants, which are also able to solve a task together using cooperative behavior. And that is also the essence of Industry 4.0 in the future, when it comes to enabling flexible production. Here too, machines must be closely networked, must work together according to appropriate rules to be able to adjust flexibly here to different requirements. We have also fitted piezo elements and MID electronics in these ants, two technologies that can be found in Festo products, in proportional valve technology, for example. Now the bionic ants have to prove whether they can also fulfill the high expectations. The ants have barely identified the object to be moved before they set to work with their grippers. Together they manage what a single bionic ant could not do. Small ant robots thus become technology platforms for the factory of tomorrow.